So let's start. Okay. Now we have seen all this in the last class. So let's go to the point where we left off in the previous class. Okay. So in the previous class, we have seen that a deterministic finite automata, or DFA for short, okay, it can be completely represented if you specify these 5 things. Okay, that is Q, which is the set of states. It has to be a finite set of states, otherwise it will not be a finite automata. Okay, sigma, it's capital sigma, okay, which generally represents the input alphabet. Alphabet is it's a set of input characters, or let's say the set of characters which make up the strings, which this DFA basically tries to recognize. It acts as a recognizer or checker for. Okay. Then a transition function, we'll see more about that. The transition function is how you transition from one state to another. Okay. Typically in a graph, the transition function is all those arcs which we draw, the labeled arcs or arrows which we draw from one state to another. Okay. And the start state, unless you know where to start, it is not completely specified. Okay, also, and we have a set of final states or accepting states. Okay, final and accepting typically are treated as synonymous, though there is a very fine demarcation between the two, which we will not discuss at this moment. Okay, and also the set of final states has to be a subset, proper or otherwise, of the total set of states. So F has to be a subset, or it could even be equal to Q. Okay, so this is the let's say the mathematical definition of a DFA. Okay, so the transition function. Now, rest of all this it's quite simple. Q is a set of states. You know that how you represent Q. That is very clear. Now, I think we have seen. I told you in the last class. Just a minute. So Q might look something like, say, Q0, Q1, okay, comma. So this is a set, or there could be more. Okay, so this is typically how you represent the set of states, where the states are named as Q0, Q1, etc. Similarly, input alphabet sigma, you might show it as A/B, or if you want to include more characters, say 0, 1 also. Okay, so this is a set. Then start state, typically it is called Q0 because that is a convention which is followed, but you can also, of course, give any name which you like. Okay, it's up to you what name you put to the start state, and the set of final states will be some subset of the set of states. Maybe say Q1 is the final state. So we would say F is the set Q1. Note that F has to be a set, okay, which is a subset of Q. You could actually, all the states could also be accepting states. Okay, so that is also possible. Now, transition function, how do we represent the transition function? So what we are looking at is basically the mathematical definitions now, okay, of something that we already know very well, what a finite state machine is or what a finite automata is. Okay, now this transition function takes 2 arguments. Okay, it's a function. Please remember, I hope you remember how you define a function. Okay, and it takes 2 input arguments, which is a state and an input symbol. So if we define that, so suppose let's go back to the graph representation. Okay, suppose just a minute. Okay, to go back to the graph representation, suppose this is a state, let's call it Q0, and we have another state, call it Q1, and we have this transition from Q0
Ma'am, you are on mute.
Okay, can you hear me now?
Yes, ma'am.
I've been talking for some time. When did you lose my audio?
Just
Like
after
5 seconds or something.
Okay. So that's not too long. So this slide, could you hear me when I came to this slide?
Yes, ma'am.
Yes, ma'am.
Just
Yes,
after
ma'am.
drawing, we
So
missed.
what we have done is I've just drawn a transition. This is a typical transition that you might see in any finite automata. So how do we represent this transition in this mathematical form? Okay, so to represent this, now usually functions, we represent functions by something called f, right? Here we are actually calling it delta, that's all. And f, usually you will have say suppose f represents some integer function, okay, maybe addition, subtraction. So what would you write? You would write plus say 2 3, so 3. So this means 2 plus 3, right? So f here, this plus is the function and 2 and 3 are arguments to the function. So something like f, you might say f a b. So these are the parameters, the input parameters. Similarly here, delta takes 2 input parameters. What are the input parameters? The first is the state, which is the current state from which the transition is beginning. Okay, so this will be q0. And what is the second input parameter? It is the input symbol on which the transition happens. So this will be A. So this transition, we would call it delta Q0A. Okay. And the destination of this transition, the state in which the transition takes you, in which you end up, that is going to be the value of this function, the actual return value, you can say, of this function. Okay, so that will be q1. So this total expression now represents this particular transition. So you can see that when you have already specified the states of the finite automata, okay, by a series of such functions, you can specify all the arrows in your finite automata or all the transitions in your finite automata. Now, once you have done that, your finite automata is completely specified. Okay, so remember, the graphical representation is all very good and it's very easy to understand also. But if your finite automata is very big, you cannot really draw a big diagram for it. Okay, and also when you are using your finite automata in your programs, for example, you are writing some code for it. So you need a mathematical representation which will be useful to write your algorithms. Okay, so this is the mathematical representation of a finite automata. Okay, so the graph representation or the diagrammatic representation, this we have, you know, already very well. So let's move ahead. This is nodes. The nodes represent the states. Arcs represents the transitions. Okay, so arc from state P to Q labeled by input symbols that have transition, or by all the input symbols which have transitions. Okay, so and then arrow labeled. Generally, if your start state, for example, is something like, it's not, is something like say Q0, then as far as the rest of the finite automata is concerned, that will be all right. But there will be an incoming arrow from outside to represent the start state. Okay, so start state is, remember, the fourth element of the 5 tuple that I discussed before. Okay, so the fourth element you have represented like this, and final states are indicated by double circles. So if the initial state is also a final state, which it could be, of course, then you will have a concentric circle. So double circles or concentric circles represent final states. So we have basically represented everything. The states by nodes, which was the first element Q. Okay, then sigma, the input elements will appear on the arcs as labels on the arcs. The arcs themselves are represented by the transition function delta. Okay, the start state by an external arrow. Okay, and the final states by double circles. So all the 5 things, when you have represented, your DFA is completely specified. Okay, now let's come to another concept, that is the extended transition function. Now, okay, now till now, whatever we have discussed, the transition function represents a single transition. But it is possible to extend this transition function to represent not just a single transition, but a series of transitions, one after the other, or a chain of transitions. Okay, so that means when we are talking of extended transition, okay, which is still represented by delta. Some people, they put a cap on it. They'll be putting a cap on it, which is called delta cap or delta hat. Okay. So the extended transition function, what it means is it is not just on a single input character, but on a string, which might be a sequence of input characters. Okay. So this is actually the mathematical definition. What it means is, suppose, for example, let's take the string ing. Do you remember that example in the previous class where we were looking at all strings ending in ing?
Yes, ma'am.
Substring?
Yes, ma'am. Yes, ma'am.
So in this case, what would you have? Say one state, another state, third state. I'm not even putting names to these states to keep it simple, because we are interested in mainly the transitions. So this would be N. Okay, this is I hope you can understand what I'm drawing. And this is G. So ing. So let's say this is the final state, this is the initial state, and let's forget all those other arcs. Okay, so this now is a transition on not just a single character, but on a complete string. Okay, so delta this, now here I would call it delta, see if we call it Q0, then delta Q0 on not just a single character, but on the string I and G. Okay, so this means the first transition will take me to this, say call it Q1. The first transition will take me to Q1, but then I have not completed the string, so N and G are remaining. So I would actually have to go from here, from Q1 to on NG. So then again, I would have to go from Q1, I go to Q2, say, okay. So Q2 and still G is remaining. So the input character would be G. And finally, the destination, if we call it Q3, that is Q3. Okay, so it is not just a single transition, but a series of such transitions. Okay, so extended transition function would represent a series of transitions on a particular, and note that these input characters are also important in this particular order. If you change the order, say I and then G after that and N after that, that will be a different string and it will not represent the same series of transitions. Okay, so the transition function, we are basically extending the definition of the transition function from a single transition to a series of transitions, from a single input character to a string. Okay, so the basis is on empty string. Okay, this is the typical inductive definition of a function. I hope you have studied induction in DMS. Have you studied induction in DMS? Proof by induction?
Yes, ma'am. In discrete math, we have
Yes, ma'am.
studied that.
You have studied it. Okay, so what is induction basically? This proof by induction, or this inductive proof, or this even inductive algorithms. If you think closely, induction is nothing but recursion, which you have implemented in the form of recursion. In recursion, you notice you have a recursion step and you have a recursion stopping criteria. Do you remember that? Without a
Yes, ma'am.
recursion stopping criteria, your recursion will go into an infinite loop. You remember that? So that recursion stopping criteria is nothing but your induction basis. Okay, and the recursive definition is your induction step. Okay, so this is exactly the same thing as your induction inductive proof or proof by induction. Here it is defined as an inductive function. Okay, which is typically implemented in programming by recursion. So the recursion stopping criteria is when your string is completely consumed up, you will you have a transition on itself. That means you stay in the same state, you do not move anywhere. Okay, and while you have a string, you look at one character of the string, Okay, and for every character you define this. Now is the transition. It is a smaller extended transition, you can see. So this is exactly what we have done here. We have consumed the string from left here. Okay, here the definition is actually consuming the string from the right end, because it is just expressing those transitions from this end to this end, but the series of transitions remains the same. Okay, so the extended transition function is just another definition. Now please be very careful in understanding these mathematical definitions. You have already seen the applications of finite state machine in creating your hardware, so you have actually applied it. Now you will also see, in fact, when you go to the next course, that is compilers, where you'll be using this quite a lot. In fact, you will see the application of this finite state machine in your programming also. We have seen an example. In fact, I'll give that example again today so that you can see. Okay, but what we are looking at is the mathematical definition, how you define this finite state machine, or this going from one state to another, transitioning from one state to another for any system, whether it's a hardware system or it's a software system, how we can express it in mathematical terms. In fact, theory of computation is largely about the mathematical underpinnings of computer science, whether it is hardware or software. And I think I have made it clear when I was teaching hardware that the demarcation between hardware and software is a very blurry line indeed. Okay, because as I always say, it is a strong statement, but whatever you can do in hardware, you can also do in software. And whatever you do in software, you can also design a hardware to do exactly the same thing. Only for some problems, the hardware implementation is a simpler one. For some problems, the software implementation is the more intuitive one. Okay, and this mathematical definition, which we are doing in theory of computer science, it basically covers all your hardware, all your software, only in mathematical terms. So if you understand this, you understand everything that you can do in computer science. Is this very clear? Okay, so in theory of computation, we'll be largely focusing on this mathematical underpinnings of computer science, let's say. Okay, so let's complete this extended transition function. So the intuition behind this we have already discussed. So convention, by convention, generally characters which come towards the end of the English alphabet, W, X, Y, etc., they represent strings. Okay, so unless otherwise specified, your X, Y, Z, etc., these are strings. And those which come from the beginning of the characters of the alphabet, English alphabet, that is A, B, C, represent single symbols. But remember, this is just a convention. It is not necessarily so. You can always override this convention. Okay. And extended delta or extended transition function is computed for a state. From a state, given a particular string, which state will you end up in? It is not just by single transition, but by a series of transition. So this extended delta defines a path. This is very important, a path. Please note that. Okay. Okay, I've messed this up, but this is a path, okay, in the transition graph by selecting a series of arcs. So this is exactly what we were seeing before. I gave you an example here. Another example is given. Only here the finite automata is given in the form of a transition table or state table, as you have seen in digital logic. Okay, so this is nothing but a state table. Only the states have been given some names, that's all. And here it is not really, we are not really bothering about which is the start state and final state. So this is not really a complete transition table or state table. You would have to, for example, give an external arrow like this to show that this is the start state. Maybe you would like to put some stars alongside some of the states to show that these are final states, and then it becomes a complete DFA. Okay, but for our purpose, this transition function is quite enough. So it means that you have three states. So Q here is equal to, what is Q? What is Q? The set of states?
A, B, C.
Yes, A, B, and C. So A, B, and C make up the set of states. Sigma is the top row, as you can see. So what is sigma? 0 and 1. So the input characters will be 0 and 1. Okay. And if you take my definition, then A is Q0 and F consists of A and B. Okay. And the transition function is from state A on input 0, you will go to the state A. That means you will loop in the same state. From state A on input 1, you will go to B and so on. Okay. And therefore, the extended transition function you can define like this. See, delta on the string 0, 1, 1. Remember input characters 0 and 1. So the string you have been fed is 0, 1, 1. Then from here, this 0 inside the leaving out the last character. So this is delta B 0, 1. Then delta B on 0. So what is delta B on 0? You can find that from here. Delta B on 0 is A. So we have substituted this by A. Okay. Then from A on 1 you go to B again, and B on 1 you go to C. So the final value of this function, if you apply it mathematically, this is what you are going to get. Okay. So this is nothing but a series of transitions. Keep that in mind. So everything will become simple. And some people denote this extended delta with a delta hat. So if you see this, let's say this representation, please do not be confused. It's nothing but extended delta. Now, language of a DFA. What is the language of a DFA? Again, something we have discussed already. So all kinds of automata define languages. Now, please do not be confused by this term, all kinds of automata. For the present, we are discussing finite automata only. Afterwards, from next class or maybe next week, sometime, SD sir will take over and he'll tell you that this type of language defined by a finite automata is just a very restricted category which we call regular languages. Okay, there are in fact many other types of languages for which also automata exist, and there are different types of automata for every type of language, and this hierarchy of languages he will explain in very clearly. Now, presently we are interested in finite automata, and you may have realized that for some time, I have been referring to these finite automata as deterministic finite automata. Okay, why this deterministic will also become very clear, particularly when we discuss what is non-deterministic. Okay, so for the present, just accept that it is a deterministic finite automata. Okay, so the language of if A is an automaton, then LA is its language. LA is the language which it accepts. Okay. So for a deterministic finite automata A, LA is the set of strings which it accepts. So what are the strings it will accept? What are the conditions? First of all, you have to start from the start state and you have to end in a final state or accepting state. Okay. So two things are important: start state and final state. So you start from the start state, and by extended delta, okay, or by a series of transitions, you consume that string. For every jump, you sort of eat up one input character, and then when your string is completely eaten up, you try to find out where you are. If you find that you are in a final state, it means the string which you have consumed is part of the language which this automaton accepts, and it is part of the language which is defined by this. Okay, so formally in mathematical terms, so LA is the set of strings W, all those strings W. So it's a set of strings such that, can you see here, this is the extend definition. So we might like to put a cap here. So for such that delta Q0, you start from the start state, W, consume the entire string, is in F. That means delta or delta hat Q0 W is equal to some state Q, and Q belongs to F. Q is in F, where F is the set of final states of this finite automata. Is this clear? the language of a finite automata, you know already all those strings which it accepts. Okay, how you are going to define it mathematically. This mathematical definition, you should be able to read this mathematical definition by now. I hope all of you can do that. Okay, now proofs of set equivalence, don't be worried about what the set equivalence means. What it means is that we are talking about two things. Okay, one is the language of the finite automata, and the other is the set of strings of the finite of zeros and ones, say with no consecutive ones. We have defined some finite automata, okay, where you do not have two consecutive ones. Okay, so can we actually draw this finite automata, draw this DFA? How many states would we require? Say for so Q0 first state. So you have to basically we are trying to recognize two consecutive ones. Actually, we are trying to not recognize two consecutive ones. Okay, so let's say Q1, Q2, and we put transitions here. So, and the input is the set, the input alphabet. So sigma is actually 0, 1. So of the 5 things we must define, one we have defined already. So, and this is the start state. So Q0 has been defined. Whenever we make this transition, we are trying to identify the set of strings of zeros and ones with no consecutive ones. So this final thing that we have put here, Q2, should not be a final state. This is not a final state. I don't know why I messed it up. It is not a concentric circle. Okay, so all those strings which take you to Q2, this is not a final state. They should be rejected. So all those strings which do not take you to Q2, they should be accepted. So that means these are going to be final states, Q0 and Q1. And from Q0, if I see 1, I go to Q1. If I see a 0, I come back to Q0. Okay.
Ma'am, why did you take 3 states?
Basically because I am trying to identify this string which I want to reject. Okay, so this string is 2 characters, so I'll require 2 transitions, so I'll require 3 states at least, right?
Yes.
See, I'm still trying to design it. I don't have it ready made here. Okay, so what I'm trying to find out is from every state, if I see 0 and if I see 1, what I should do. So if from Q0 I see 0, okay, I'll stay in the same state. So what exactly do these states mean? So Q0 basically means I have seen 0 number of ones. Q1 means I have seen 1, 1. And if I see another 1 immediately, then I'll go to Q2, which is actually the rejecting state. Okay, so if I see 0, I stay here. If I see 1, I go here. Then if I see a 0 again, that means my string is still acceptable. So I go back to Q0. Okay, and if I see 1, I go to Q2. That means now I cannot keep on accepting this state, this string anymore. And in Q2, if I see 0 or if I see 1, it doesn't matter what I see now. Actually, I'll have to keep on rejecting that string. So I can keep on looping in Q2 as long as I like. But since I have seen these 2 consecutive ones at some point, I have to reject all those strings. So this now would be a deterministic finite automata which accepts the language in which no string has 2 consecutive ones. Can you see that? Are all of you convinced?
Yes, ma'am.
Yes,
Okay.
ma'am.
So
Yes,
and
ma'am.
notice some important things about this automata. First of all, whatever state we are in, we know exactly where to go for every input symbol. Okay, so there is a deterministic path I have to follow whatever input stream I get, okay, whether it is an acceptable string or it's a rejected string. So this you can say is a kind of sync state where all the rejected strings end up. Okay, and these are the two final states. So have we defined all the 5 things? Now that our automata is complete, we know that Q is actually Q0, Q1 and Q2. Can you see that? And F, which is a subset, that is a set of final states, which is a subset of Q, is going to be Q0 and Q1. Okay, so Q is defined, sigma is defined, the transition function is defined as in the form of arrows in this diagram. Okay, initial state has been shown and the final states have also been shown. So this is a complete DFA, and it rejects all those strings on 0 and 1 which have 2 consecutive ones. Okay, so this is the equivalence. The equivalence is just a definition and what the finite automata is actually doing. Okay, so this is the language accepted by the finite automata. Now, how do we suppose we have been given 2 different finite automata? Now, how do we state that these 2 finite automata are actually equivalent? They are doing the same thing. What does it mean when we say that 2 different finite automata, 2 DFA, do the same thing? Okay, they are doing the same thing if they are accepting the same language, if they are recognizing the same language, which means that every string which is accepted by one finite automata will also be accepted by the other. Okay, and there will be no string which is accepted by one and rejected by the other. Okay, so if this is the situation, only then we can say that 2 different finite automata accept the same language. It is the language which defines the functionality of a finite automata. Okay, so here you can actually define many finite automata which will accept exactly this same set of string, that is no consecutive ones. Okay, what we have seen in the previous slide is just one example. In fact, it is the best example. Why it is the best example, again we will see later. So this is about, okay, now all these languages, all these, so any language which is accepted by a finite automata, you can see that it forms some kind, has some kind of regular pattern to it. All the strings of this language, they follow some kind of pattern. Okay, for example, all the strings might end in ing. Okay, or in the last case, all the strings will have, if you check, go through the strings, you will never find 2 consecutive ones. Okay, so that itself is also a pattern, please remember. Okay, so these are regular patterns, and the finite automata accept languages which are called regular languages. Okay, so a language accepted by some finite automata, it is called a regular language. Sometimes you might also encounter languages which are not regular. Regular languages are actually a very restricted class of languages. Okay, typically you cannot define a regular language by some counting measure like using n or something. Okay, so regular languages cannot count to arbitrary high integers. That means any arbitrary integer we do not know what. Suppose you say a string of 7 consecutive A's. Is it regular or non-regular? What do you think? We have been discussing regular languages for 2 classes now, so you might have developed some kind of intuition. What do you think? Say, I say that
it's regular.
It is regular. Why? Because first of all, 7 is a small number. Okay, even if it's not a small number, if you define a specific number, you can always create a finite automata to accept exactly that number. But if you say n number of A's, n, you do not know what it is going to be. It could be small, it could be big, it could be arbitrarily big. Okay, and it is not clearly defined, it is not predefined. Then n is not regular because it really cannot keep a count of any number which you specify. Okay, so sometimes when we say that a regular languages cannot count, and then I give you a pattern like say A7. That means 7 consecutive A's. Why I'm fixing on 7, I do not know. It could be A3 also, okay, or 03. Then it would be something like this. So you say that, madam, this string is counting. It is counting for three zeros. But then why is it regular? It is regular because this 3 is predefined. It is not going to change, and it is not too big. Okay. Of course, even if it is big, say instead of big, if it had been 300, then it would still be regular, because it might be difficult, but I can still draw a finite automata which accepts 300 zeros one after the other. Okay. So as long as it is predefined, it is regular, but it cannot be arbitrary. So arbitrary counting is not possible by regular languages. Okay. So that is one intuition which you have to realize. This I think we have seen before, but then we can see it again. So some things are easy with finite automata. For example, identifying certain substrings. Now this identification may be to accept, or it might be to reject. For example, in the previous case, we have identified the substring 11 in order to reject it. Okay. Then subsequences. What does subsequence mean? That means in between there could be other characters. Okay. So it is not consecutive characters, but these characters appear in some sequence. Okay. Maybe interspersed with other characters. Then some kind of modular counting. Small number, predefined numbers. Say odd number of ones. Now, odd number of ones, again, this is something students often get confused about. Madam, odd number can be arbitrarily large and not predefined. So can it still be regular? Actually, it could be regular. Odd, even, etc. These are nothing but multiples of 2, right? So it still can be defined as a regular expression. Okay. And some things are impossible, like equal number of A's and B's. I think we discussed in the last class why it is not possible, because you would have to keep account of how many A's and how many B's. Then more zeros than ones. Again, you require to keep a count, and you do not know how many more. Okay, so you cannot really call this a regular language. It cannot be expressed using a finite automata. But some things can be done with finite automata, and it's very important. So it's a very important way of recognizing certain patterns. Non-regular languages, some examples: 0 and 1n. Okay, a certain number of zeros followed by equal number of ones. You cannot keep a count. Then set of strings. Okay, so this again, the set of strings. This is exactly the same one. Okay, so this is a non-regular language. Another example is, again, these are some of the typical examples which you cannot express as a regular language. So strings in which the brackets, okay, we are here just looking at round brackets. These brackets are balanced, okay, such that W is balanced. Now, the alphabet here, we are ignoring all other characters in the string. We are only interested in the left bracket and the right bracket, as you can see. So this left bracket here and the right bracket here, and balanced parenthesis. So when we say that W is balanced, what does it mean? It is balanced parenthesis. You know what balanced parenthesis mean. Okay. So are those that can appear in arithmetic expressions. Okay. So these
number
are
of open brackets and closed brackets is same, so we cannot compare them.
I beg your pardon?
Ma'am, will it be like an irregular one, because we have to compare the number of open and closed brackets? So
actually, you have to keep a count. You cannot, for example, suppose you have an expression, say, is this a balanced parenthesis?
no, ma'am, because you count
Obviously not.
three.
Now here,
No.
now when you reach this point, you might find that the number of left brackets and right brackets are actually the same, but this is still not a balanced parenthesis. It's not a balanced expression, right? So you have to keep a count at every point of how many left brackets you have seen and the number of right brackets should be less than the number of left brackets. So that is the, you can say, the definition of a balanced expression, right? So this is not acceptable, but something like this, have I balanced it? Yes. So this is now acceptable. Okay. So that means at every point you do not know how many left brackets you should have kept a count of. So that is why you cannot, this is not a regular expression. Actually, it is very difficult to define in exact terms what a regular expression is and what a finite automata. The definition of regular expression itself is with respect to a finite automata. Everything that a finite automata can accept is a regular expression. Okay. So, but this intuition, suppose you are given a particular language, you are given a definition of a pattern, to try and understand whether you can, whether it's regular or not, try to find out whether you can draw a finite automata for it or not. If you cannot, then it is not a regular expression. Okay. Because these are going to be questions that you will be facing regarding this classes of languages. But some languages are regular, and for them to be able to draw a finite automata becomes a very useful skill. Okay. So for example, this is actually a very important example, and you can imagine that this example you are going to encounter when you study compiler design, when you try to design compilers for programming languages. Okay, so all the strings that represent floating point numbers. Okay, you know that floating point numbers can be represented in many different ways, and these strings which represent floating point numbers, integers are too easy actually. Okay, floating point numbers, they will often have something like e or e to represent the exponent, etc. But still the pattern is actually a regular pattern, and you have to draw a finite automata for it, or you have to implement a finite automata for it in programming to be able to recognize a valid floating point number. Okay. Of course, integers and names, etc. Those are too simple. Even your password, for example, when you are asked to give in a password, sometimes you might be you might have restrictions like a password has to begin with an alphabetic character. Then you should have at least alphabetic and numeric characters, and maybe some special characters, and you should be at least 8 characters long, etc. So these kind of patterns are typically regular patterns which can be represented by regular expressions, and you can actually implement a DFA for it. Okay, so whether or not your password is a valid password, typically a DFA will be checking. Okay, so when you try to input a password and you find that it is not really being accepted, it is because the DFA has rejected it. Please remember that. Okay, the checker is nothing but a DFA. Okay, and this also, I think something like this will be coming back to later, so let's not go into the depth of this. And this also we have seen before. I put it here again so that now you relate to what we have seen. So these are nothing but the strings which end in ing. Okay, if the strings end in ing, you end up in the final state. And these finite automata, till now you have the only way you have implemented a finite state machine or a finite automata has been by a sequential circuit. Now you can see that you can also implement it using programming languages, any programming language of your choice. Okay. So now let's come to non-determinism. How much time do I have left? What time does this class end?
Ma'am, 5:10.
All of you speak at the same time. I can't hear you. What is the time?
Ma'am, it ends at 5:10, ma'am.
5:10.
Yes, ma'am.
Okay, then I have already overshot. Do you have a class after this?
No, ma'am.
Okay, then please give me another 10 minutes. I will not extend it beyond another, say, 5:30. Okay, because there is such a huge lot to cover. So let's actually move on. So now I told you that we have been referring to these finite automata as DFA, or deterministic finite automata. Now, what is a deterministic finite automata will become more clear when we discuss what is meant by a non-deterministic finite automata. You can also have finite automata which are non-deterministic. So what does non-determinism mean? Okay. A non-deterministic finite automata, or it is actually called NFA for short. So from now on, if you encounter these acronyms NFA and DFA, you should understand what they mean. Okay, DFA typically means deterministic finite automata. NFA means non-deterministic finite automata, and we'll be using this very much. So be very clear. A non-deterministic finite automata has the ability to be in several states at once. That is very confusing concept. Okay, so transitions from a state on an input symbol can be to many states. Okay, so what it means is, suppose I have a state here, let's say, let's call it Q0, and I see the input character, say 1. Okay, and I find that there is not just one but two different next states. Say let's call this Qi and let's call this Qj. Okay, and to both these next states I have transitions on 1. So what do? What would you do? You are presently in Q0 and you are seeing the input 1. So what would you do at this point? So that's difficult, isn't it? So what you can do is, actually you can be in both Qi as well as Qj. So what we will do to be practical is, we will check out both Qi and Qj, maybe not at the same time, one after the other. Okay. Or we will do something called a breadth first search. Have you studied BFS already? Do you know what is breadth first search?
Yes, ma'am.
Okay, so till now what we have been doing is, whenever we saw a state, we had exactly one next state to go to on a particular input. Now we find that on a given input we have more than one states. So what we will do is, we will explore both the states at the same time, or maybe one after the other. Okay, so non-deterministic finite automata is one in which the next state is not uniquely defined. You can have more than one next state for a particular state, for on a particular input character. Okay, so that is the most important feature of non-determinism, where the next state, a transition on an input character, can take you to not just one state but a set of possible next states. Okay, so in such a situation, now you can see that working with an NFA or transitioning through an NFA is a little more difficult. So how do we do that? So let's take an example. So what we are defining here is a set of all strings with two consecutive A's or two consecutive B's. Two consecutive A's, or, this is important, or two consecutive B's. So that means there are two possibilities. So two possibilities means basically two parallel paths to a final state. So you can see from this initial state here and to this final state here, there are two parallel possible paths. Okay, so one path in which two consecutive A's are accepted, the other is two consecutive B's are accepted. So if you see an A or B, you know where to go. But maybe the these are not two consecutive A's, but AB, something, a string like say A, B, B, A. Will this be accepted? What will be the path you will follow? So A, B, okay. You really do not know where, if you should loop or if you should take this transition. Once you have taken this transition, if you see a B again, you have nowhere to go. Okay, so non-deterministic finite automata is where every single next state is not uniquely defined. Sometimes there is no next state at all. For example, from the state 1, okay, the state here, you do not have a next state transition on B. And from this state here, 0, you have two different transitions on A and two different transitions on B. So which should you take? Actually, what you should do is you should try both options, not just both options. Sometimes it will be multiple options. And if any of these options take you to the final state on the consumption of this entire string, then this string is accepted by the finite automata. So you can see the set of strings accepted by the finite automata is a little more complex now. Okay, sometimes the next transition which you should take is clearly defined, and sometimes the next transition which you should take is not clearly defined. Sometimes it is not defined at all. Sometimes it is multiply defined. Okay, so which would you prefer to work with? If you had to use a finite automata, what kind of finite automata would you prefer to work with?
Deterministic.
Certainly. Okay, so if you are asked to implement something, to check for something, you would always hope that the finite automata which you are given, the checker for the finite automata which is the checker, is a deterministic one. Okay, so implementation point of view, please note that we always want a deterministic finite automata. But now, when you are being asked to design a finite automata, suppose you are given the specification in something like this in English-like language, a set of all strings with 2 consecutive A's and or 2 consecutive B's. So here, drawing this finite automata might come more naturally. Okay, so this kind of finite automata is what is called a non-deterministic finite automata. Fortunately, we have means by which we can convert this non-deterministic finite automata into a corresponding deterministic one. All non-deterministic finite automata can be converted to deterministic finite automata which accept exactly the same language, okay, which are equivalent. So that is where the concept of equivalence of finite automata comes around. Okay, it is possible to convert one finite automata to another without changing the language which it accepts. Okay, so now you know why those were called deterministic, because they have special good characteristics. Okay, but here this is a non-deterministic finite automata. Note that some states have an empty transition on A and some have multiple transitions. Okay,
Hello,
so
ma'am.
you start. Yes. Yes. Do you want to ask anything? Anybody?
I have a confusion in previous. Yes, ma'am. Yes, ma'am. I want to ask something.
I can't understand what you're saying.
Hello, ma'am. I want to ask something on previous slide, ma'am.
Previous slide? Okay. Please ask.
Yes, ma'am. Ma'am, can we draw the state from 1 and 2 between when I got B on a state 1, I go to a state 2? Is it okay?
I'm not able to understand what exactly you mean. You want to add some transitions to this finite automata?
Yes, ma'am. Yes, ma'am. I want to transition from state 1 to 2 when I got B. Is there any problem?
The problem is it will change the language. It will change the automata. It will change the language which it accepts. Okay, there's no problem. You can keep on drawing anything you like. But the thing is, if you want the automata to continue to accept the same language, then you have to be careful what transitions you put. What you are saying is, okay, let me just get rid of all this. What you are saying is possibly that you want to add a transition here. Is that what you are saying? Is this the
Not
transition
visible
which
to
you
me.
want to add? No, I cannot understand what you're saying. I think what you meant is that if you add a transition from one state 2 to here, 1 here, okay, then will it change the language? You have to see what strings are now being accepted. Let's first discuss how an NFA accepts strings. Then maybe we'll come back to your question, or maybe your question will get answered automatically. Okay, so let's talk about non-determinism. So let's start in a start state. Except if any sequence of choices leads you to a final state. So a string is accepted if there exists a path from the start state to the final state for that string. Okay, there could exist many different paths in the finite automata. Please remember, okay, because we have a choice. Often we have a choice of next states. So there could exist many different paths from the start state to various different states in the finite automata for a given string. But if any of these paths end in the final state, then the string is accepted. Okay, so basically it is not for all, rather there exists. I hope you understand this, for all and there exist. Okay, for every path you may not end in the final state, but if there exists a path which takes you to the final state, then that string is accepted by the finite automata. Okay, so basically what you are doing is you are trying to guess. You may be successful the first time. If not, you can be successful in the second time. Or what you might do is all the paths you might try to explore parallelly. That is your breadth first search. That's why I asked if you know what is breadth first search. If you check in breadth first search, when your string is consumed, the complete string, say B, A, or something, okay, when your string is consumed up, you find that you have landed up in, say, 3 different states in the finite automata. If any of these states is a final state, then the string is accepted. Do you understand what it means by accepting a string in an NFA? Okay, please remember.
Could you repeat the last point once more, ma'am? I didn't get that one. Like the breadth first
Suppose you
search part.
start from, okay, let me do some cleaning up work here first. Okay. Suppose this is my start state. Okay, let's call it Q0. And then we have been given the string, say BAA. Okay, and we start moving in this finite automata. It has a series of states, many different states, and it's got a complicated graph. Okay, so BA, you find a path through this, and you find that one of the paths takes you somewhere to this state. You end up in this state. Another path, you know that there can exist multiple paths. So another path takes you to this state. So this is another state which you end up in. And a third path possibility, maybe that path diverges from here and it takes you to this state. So 3 different states in which you can end up, okay, on the string BABAA. So now what you have to do is, this is your breadth first search. You have been doing a breadth first search at every point, every possibility you are exploring in parallel. You are exploring at the same time. And in doing so, you have found these 3 different paths and 3 different states in which you end up in when your string has been completely consumed up. Okay. Now, if any of these, at least one, happens to be a final state, then the string is accepted by the NFA. It does not have to, you do not require that all of these states should be final states or accepting states. If any of these is an accepting state, then the string is accepted by the finite automata. So what it basically means is, let me complete. What it basically means is that there exist multiple paths. One of them, at least one of them is going to be the correct path. And we can always be optimistic that the NFA will be able to guess the correct path. Yes, now you ask what you want to ask.
Ma'am, what if what if 2 possible paths lead to accepting states?
2 possible paths. Fantastic.
Yes.
We need at least one.
Okay. So that is also valid. Okay, ma'am. Thank you.
Yes, absolutely. It is possible that all the paths lead to accepting states. Okay. So this is non-determinism, where there exist multiple choices and at least one of them will be the correct one. And you have to be optimistic that your first guess will be correct. If not second one, at least early guesses will be correct. But if not, you have to keep on checking every possibility before you can say that a string is not accepted. Okay, so saying yes is easy, saying no is more difficult, because you cannot say no, this string is not accepted until you have checked every possibility. Does this answer many of your questions? Is this idea clear to all of you, how an NFA accepts a string?
Ma'am, if more than one path leads to accepting state, we can follow any of the paths, right?
Any of the paths, if they are valid paths, you understand what is a valid path, right? Every transition will consume one input character. In
Yes.
order, of course, left to right. Any other doubts at this point about NFA?
No, ma'am.
Okay, so then the formal definition of a non-deterministic finite automata, okay, it is almost the same as before. So Q is the same. Just a minute, please. So Q is the same. Input alphabet means the same thing. Transition function is defined in exactly the same way. Okay, but there is a distinction here which we'll see. The start state and the final states are also defined in exactly the same way. So what is the difference? This difference is in the transition function. Previously, your transition function was defined as delta, say QA, Q1A, it goes to Q2. So this was the kind of definition you were seeing in case of DFA. But now remember, in case of NFA, the next state which you go to, there could be multiple next states. So this is now not a single state, but rather a set of states. It could actually be something like this. Okay, so for a given state on a particular input character, you might be able to go to several different next states. So the transition function means the transition function delta here is now slightly differently defined. Okay. As far as this, okay, this induction is the same as before. This is defining delta hat. Okay, so the language of an NFA, a string is accepted by an NFA. This is what we have already seen. This is accepted by an NFA if delta Q0W contains at least one final state. Okay, multiple final states possible. At least one has to be there. If there exists a sequence of valid transitions from Q0 to a final state, then the string is accepted by the finite automata. So the language of NFA is a set of strings it accepts. I hope you understand the difference between NFA and DFA. Please remember, our ultimate target is DFA. Okay, but sometimes we have to start with an NFA because it is easier to draw an NFA than a DFA at the first attempt. Okay, in the next class, we'll start with NFAs with epsilon transitions. Today we'll stop here. Thank you very much.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, and you may leave.
Ma'am, after the chapter ends, will you be giving the notes or will you be giving them now only?
I think you have it's a recording is on, right? So whoever
Yes, ma'am.
started the recording, please stop it also. You look at, just a minute, let me stop the recording.